Hi, everybody. It's Dr. Chabot, and we are going to be talking about RL circuits. So to start, let's talk about inductors and inductance. So remember that inductance is N times the magnetic flux inside something, inside a circuit element or inside a loop, because of the current through that loop. So for example, let's take an inductor that we're going to draw like a solenoid, and that's actually the symbol that we'll use in circuits. And let's say that there was a current through that inductor. This current creates a magnetic flux inside the inductor. And then what that allows us to do is to say that if the current changes, then the magnetic flux through it changes. And so what we have is a relationship with Faraday's law, which remember tells us that you get an induced EMF that is going to oppose that change in flux. So it creates a magnetic flux inside of it. So a changing current gets an induced EMF. And the inductance then is a property of a circuit element or of an item that tells you how much magnetic flux is created given some amount of current, because the larger that magnetic flux, the larger that that induced EMF will be, and then therefore the bigger impact it has on your circuit. And so the solenoid is the standard one. And so let's go ahead and look at the L of a solenoid. We did this briefly already. And so the L of a solenoid is going to be equal to the number of turns of a solenoid times the magnetic flux through the solenoid, which is going to be the magnetic field times the area times the cosine of the angle between the area and the magnetic field vectors divided by I. So this is, I've just plugged in for the magnetic flux from the above equation. And then note that because the area vector, if we look at a solenoid, which again is just, I'll draw sort of a larger one, right? Then our area vector is going to be parallel to our magnetic field vector. And so that cosine of theta term is just going to be cosine of cosine of 0. And so cosine of theta becomes 1. And so then what we can do here is actually then plug in for our magnetic field from a solenoid, which from the equation sheet is mu naught, and then times I times N, which is the little n, and remember that equals n divided by the length of the solenoid. I'm now going to use curvy L to denote that length so that it doesn't get confused with capital L for our inductance. And then I'm going to multiply that by A because of the A in the equation above, and then divide by I. So I've just plugged in for B. We can now see that when we do this sort of derivation, the current drops out of this, and the inductance of a solenoid becomes solely a property of the solenoid itself. So mu naught, meaning what's inside the solenoid. If it's air, then it's just mu naught. If it's iron, then it would be the mu of iron. So mu naught times n squared, which is the number of turns squared, and then times the cross-sectional area of that solenoid, divided by L, the length of the solenoid. And so this is a property of the object, like capacitance and resistance. So it is another type of circuit element that we're going to use. So when we talk about RL circuits, then we're going to look at direct current, so DC. We're not going to do AC circuits in this class at all. So we're going to look at direct current, and then I'm going to look at a series RL circuit, meaning that I'm going to put a resistor R in series with an inductor L in a direct current circuit. So I'm going to have a resistor in series with an inductor, And then we're going to start by looking at the case where nothing has happened yet. I haven't closed a switch. I'm going to have an EMF, a source of EMF, which again is just a fancy way to talk about my voltage source. So I'll have some EMF of my source. I'll have some resistor R, and I'll have some inductor L, and then I'll have the switches initially open. And then what's going to happen is at t equals 0, we're going to close the switch. And then that's going to have the source of EMF create that potential drop across the R and L. And we're going to see what happens in this scenario. And so this is going to be what I call the current rising phase. So current rising. And here's what's going to happen. Basically, I'll tell you the ending and then we'll write down the equations for it. Basically, what's going to happen is this current's going to flow through the inductor to start, and the inductor is going to basically just not want that to happen, right? It opposes the change in anything that's going to happen. So it wants it to stay the same. So initially, actually, the current's going to start at 0, and it can't initially jump up all the way to the starting point. So if there was no inductor, and I turned this on and I plotted the current versus time, then let's say it was off, and then over here I open the switch at, say, let me put my t equals 0 a little bit offset, then we would just have this instant current, right? The current instantly would turn on if we did not have an inductor. So that's without an inductor. It would be the instant current. And when we say instant, again, that's like the speed of light because it's the speed of the electric field. But with the inductor, then what happens is we're going to get the current versus time. The inductor is going to fight this change. And so what we actually get is the current's going to rise up more slowly as the inductor fights the change. So the inductor fights that change, and it causes the current to rise more slowly. So basically, the idea that what an inductor does is it causes it to resist change. It definitely does not like the instant rise that in current. And so it's going to set up a back EMF that is going to oppose that change. So initially, what happens if I'm going to go up to this original diagram and I'm going to draw my current as a function of time, then if I go ahead and I'll just draw it over here in this branch, I as a function of time headed into the negative side of my EMF. The inductor really doesn't like this. And so what we end up with is it creates what we call a back EMF. So a back EMF is going to work such that it's setting up its own EMF that then is going to be opposing that change in that current. So initially, a key point here is that initially the voltage across the inductor is equal to E, which is the maximum value. So the inductor wins to start, basically. So the inductor gets it all to start. And the voltage across the resistor, because the inductor took it all, is going to be 0 because there's no current flow, right? So that's going to be the minimum value. And so, there's essentially no current flow to start because the inductor is resisting it. So the inductor is fighting that change in current and then causing there to be no initially any current. Now remember that V sub R equals IR. So this means that I sub R equals 0. And again, these are all initially in this current rising phase, right? This is why we call it the current rising phase. So the voltage across the inductor is the maximum value, which means there's really no current through the circuit at all. And then what's going to happen is we're going to end up with the final scenario, and I'll use a different color for that here, which is going to be and by final, I mean after a long time has passed, right? So after a long time, then we're going to have the case where V sub L is going to be equal to 0 because there's basically no change after a long time happening. It's fought it and it's fought it and it's fought it. And then eventually the current gets up to the V equals IR and there's just no change anymore. And so it's going to start to approach 0, the voltage across the inductor. And then after a long time, it's going to be as if the inductor wasn't there. So as if the inductor was just a wire is how you can analyze that part of the circuit. The voltage across the resistor will get all of it. That'll be the maximum value. And that's going to be once you have essentially what we call this steady state. So the inductor can only fight it off for so long. It can't completely stop it. If it stopped it, there'd be no change and the inductor would stop fighting it. And so the idea that you have this opposition, but it's never going to quite win. The inductor always loses. It tries really hard to start, and it always loses. And, eventually the resistor will get its full voltage across it, and the current through the resistor, V equals IR, will just be equal to my E over R, my EMF over R. Okay, so now let's go ahead and sketch these. So if we go ahead and sketch what we expect for the voltage across the resistor, and the voltage across the inductor, and the current through the resistor as a function of time. And again, this is going to be for what I've called the current rising phase. Then let's start with the voltage across the inductor. So the voltage across the inductor, remember that it wins. And so this is going to be the voltage across the inductor as a function of time. It's going to start off with the EMF. So initially it's winning. It gets it all. But eventually it loses to the resistor. So it gets it all to start, and then it loses that. It's never going to completely have it all, because if it had it all and it just kept it all, there'd be no change. There'd be no inducing. And so then we would have, everything continue to move again. And so everything is kind of like when you imagine dropping the magnet through a copper tube and the magnet continues to fall and fall and fall. As it's going, because you can never completely stop it, or else that induction effect stops. You need a change in time. So initially the EMF is all across the inductor. And then remember that we're going to have, and I'll write it down here, VL plus VR has to be my total EMF, right? That's going to be our conservation of energy, just like we did with previous ones. And so if we go ahead then and we look at the voltage across the resistor as a function of time, it initially loses, but it is eventually going to win. And then it's going to come back up to that maximum value. And at any given time, they're going to add to that total. Now, remember that the current, right, is just, again, from their I equals VR, is just equal to V over R. And so the current as a function of time is also going to rise. That's why this is the current rising step. And it starts at the EMF over R as our final value, and it'll move up and exponentially rise. So just like we did with RC circuits, we look to see whether it's a rise or a decay. So this is a decay, this is a rise, and this is a rise. And so then we write the equations very simply by saying, okay, my voltage across the inductor is going to be my maximum times my decay term, e to the minus t over tau. And I'll come to this tau in a second because there's going to be a tau that depends on our circuit elements, L and R. And then here I would have the voltage across the resistor would be equal to the maximum EMF, and then times my rise term, which is 1 minus e to the minus t over tau. And then over here, I would have my current being the same thing. So my current would be my maximum current. You could call that I naught, but I'm going to write it in as EMF over R times 1 minus e to the minus t over tau, which is my rise term. And so an important part of this is our time constant. So the time constant, and this comes from solving these differential equations that we get when we write out our loop rule and all of that. But for now, we'll just tell us that the time constant for this circuit is equal to L, the inductance, divided by R. So the bigger the resistance, then the smaller the time constant. And the inductor, the bigger the inductance, then the bigger the time constant, the more it can fight. So it's kind of like a war between the inductance and the resistance. They're not complementing each other, they're fighting each other. So you get this L over R behavior. So that's the current rising situation. And again, the two voltages add together so that the total is always that source voltage at some amount of time. Okay, so now let's go ahead and look at the current decay. So if I kind of just zoom out to see all of this, so the current rising here, we had attached it to an EMF, and then we closed the switch, and it fought and fought and fought the current rising, but eventually the current rised up. So now let's say that I'm going to take this circuit, and I'm going to start, so let me put it in the resistor here, and I'll draw my inductor again. So there's my R, and there's my L. And what I'm going to do now is I'm going to basically short out. So I'm going to move kind of a switch here to where my EMF was or is, right? So initially, I'll call this, say, switch 1. That was closed. But now let's go ahead and assume that I have another switch over here, which I can call 2, so that it's like this. So what I'm going to do at this point is at my new t equals 0. So now at t equals 0, I'm going to open switch 1, and I'm going to close switch 2. So I end up with 1 open and then 2 closed. So it's going to be essentially as if that middle EMF is no longer attached, and I just have an inductor and a resistor in series with themselves. But the inductor has that energy. It has there's a current flowing in this circuit. So there is a current flow that's going to be happening in this circuit. So initially, there is a current flow. To start. So this is going to be our current decaying phase. So this is going to be our current decay, because what would normally happen, let's talk about that again, without the inductor, then what would happen for my current as a function of time is that my current, when I change these switches, I start off with some max current, it's going to drop down to 0. So I'm going to go ahead and kind of redraw that with a different color. So if I have my current as a function of time, initially it starts at some value, I flip these switches, and it just shuts off. We just instantly shut off the current. But with the resistor, with the inductor, right? Then my current as a function of time, it initially has some value. And again, inductors don't like sudden change, whether it's turning something on or off. So the inductor is going to fight that change as much as it can. And so it's not going to let it instantaneously change down. And instead, the current's going to decay down because the inductor is fighting that change. So what we can do then is do the same analysis that we did before. We can say to start, and we can look to see what's going to happen in this scenario. So initially, to start, the voltage across, let's start with the current, because we know the voltage across the resistor is going to be equal to the EMF. It's at its max value. And the current across the resistor is our EMF over the resistance. And again, that's at its max value. So what happens across the voltage across the inductor? Well, notice, right, that when I remove that source of EMF, VL plus VR have to equal 0 in this stage because I took out the source of EMF. And so what that means is that all of a sudden there's this current through the inductor, but it's trying to decrease. And the inductor is actually going to set up an opposite EMF to oppose it. So it's going to get negative E instantaneously. To start, because it all of a sudden has no source of EMF, it's going to instantly change which is positive and which is negative. And so you actually are going to have, remember from our Kirchhoff's laws, if my current's flowing through the resistor like this would be my positive and my negative side of the resistor. Then the inductor is actually going to switch and try to oppose that. And it'll be a negative and a positive. It's opposite of what it was when it was attached to that EMF. So those all happen instantaneously. And we end up with having the plots that we'll show below. So let's go ahead and sketch these. So we can sketch our V sub R, and I'll do it in the same order I did before. So let's start with our VL as a function of time. And what I'm actually here in order to do this, we're gonna just kind of go on to our next page because our VL comes all the way down to the negative E. And then eventually what happens is the current does stop, right? Like I put it in the circuit and I took out the source of EMF. The current's not going to flow forever. There is going to be your energy dissipated through that resistor, but the inductor is just going to fight that change. So instead of it happening instantaneously, it then is going to happen and decay. So this is still a decay term, but again, it's down at negative epsilon naught to start. The voltage across the resistor is more of our standard one where it starts at our maximum EMF, but again, it's going to decay. And then again, these are all as a function of time. And the current through the resistor is also going to decay. It starts off at the E over R, and it's going to decay down as well. So these are all decaying in the decay phase. So that's handy. And let's write out the equations for that. And so the equation here, again, we do the same thing. We take our maximum. It happens to be negative, so no big deal. So we would write the voltage across the inductor is equal to negative EMF times my decay term, e to the minus t over tau. And then over here, we have the voltage across the resistor is equal to my maximum, which is positive E, and then my decay term, e to the minus t over tau. And then likewise, my current through the resistor is going to be equal to EMF over R, and then my decay term, e to the minus t over tau. So in the current decay, It's easy because literally everything decays. The weirdest part is that the inductor instantaneously switches its voltage down to negative because it's opposing that decay now. Before it was opposing the rising, and now it's opposing the decaying. And so that switches, right, from Lenz's law. It's going to switch the EMF that's induced, and you have that now back EMF opposing that change. Okay, so that is what we need to know about RL circuits. We have 2 times the current rising phase, where the current rises. If you remember it as the current rising phase, that's pretty easy. The current rises, the voltage across the inductor decays. The time constant for both current rise and current fall is going to be this. And again, when we use this equation for our time constant, we're using the equivalent resistance here, Req, for that time constant, just like with RC circuits. Okay, so you should be all set then to work through some of the problems, or that one problem I posted on your own. Okay, good job.